Hope you've all gotten your hotel arrangements set up. So today I'm going to streamline a little bit. We're going to pass by any further discussions of these sort of almost RAND qubits, not quite good qubits, interesting but not optimal qubits. And so I'll mainly review for you today the current developments, say within the last 5 years approximately, of what is today the sort of best qubit system. And I say system because now there are experiments. Well, there's a paper doing full quantum circuits in 3 qubits, but with promises of 8 qubits and 13 qubits soon to come. So it's worth it for you to know what those systems are, and I'll give you some notion of why they'll be successful. And I'll go through some derivations today, but I'll also be at some points talking a little bit qualitatively about these things. So I'm going to return to transmons, and that I think I'll stay the whole morning with transmons. I mean, if I indeed finish everything, which I think is very unlikely, then I could go back to some interesting comments about other qubits that I didn't get to tell you. I'm looking for the eraser to get rid of the notice here. Any clues here? There were 2 of them around here, so someone comes to the rescue, because I want to immediately begin by writing down a qubit Hamiltonian. Seems like they were. That's true. Okay, yeah. I guess we're given the camera. I can start writing anywhere. Start writing upside down, and the camera can rotate. Anything you want. Anyway, you can keep looking. Hey, there we go. Huh? Thank you. Okay, great. So I'm going to write, again, the transmon Hamiltonian. I'll just use a little bit different notation, and I've rescued a few factors of 2 in this. So we'll be talking about this. This is where some new factors of 2, actually a factor of 4, if you really follow things carefully. And I'm going to write things like this because this was capital Q before, but now we've pulled out some factors. So I use this often in the literature, and in fact even in the notes in front of me. This is given the symbol n because it is some kind of number of Cooper pairs, but I dislike that very much because in a few more lines, like about here, there'll be another thing that's clearly a number operator, and it's not that operator. So that's why I want to keep them distinct. It's yeah, okay, I'm starting to put hats on, which is sort of also a reminder. Whoops. I'm putting hats on things to remind you and myself what things are operators and what things are not in this setup. So at this point, this is not an operator. Actually, it's going to become an operator in a short while. So that's the reason for my slip there. Okay, minus EJ cos phi. So that's what we're going to base things on. Transmon is such a beautiful, simple thing. Well, it's also the Cooper pair box mathematically is a simple thing. But what we learned yesterday is that for this transmon regime, EJ much greater than EC, then this thing is nearly harmonic. So one thing that's useful to do is simply Taylor expand this cosine so that you get 4EC, all this stuff, Q minus Q offset squared. And then if I get the constants right, I'll forget about this constant, plus 1/2 EJ phi squared. I'll write one more term. Actually, it's a minus. That's actually pretty important. Minus EJ over the factor 24 phi to the 4th power. And let's stop there. So we're doing a pretty good approximation of the quantum mechanics of this problem. Let's remember, and this just be useful for notational purposes, that when we have a Hamiltonian like that, that there's a useful representation, and we're going to transit into sort of an optics, a second quantized representation of this, where I introduce creation and annihilation operators. Remember that this, of course, or this part, of course, will have the spectrum of a harmonic oscillator. So I can introduce the usual operators that will move me up and down in this ladder. So I'll have these things, so there's B dagger, which is an operator that moves me up one in this ladder. They have, and sorry, I don't have the constants written down here, but you would write Q as some combination, well, phi and Q would be written as the different Hermitian linear combinations of these. So this is proportional to B plus B dagger, and this is proportional to I times B minus B dagger. As I say, the two different Hermitian operators you can make of these things. And the point of this is that when you get the constants right, then you have a simple way of rewriting this. And this was a factor that I should have mentioned yesterday, but I didn't. 8 ECEJ. And then it's B dagger B. I have here plus a half, which of course I don't really need. And then there's also, I could go further with this. I won't in the present lecture, but I can rewrite this term so it has a form something like EJ over 12 B plus B dagger to the fourth power. So there are, this actually, when you keep track of the constants, this is in fact an EC here, because I mentioned yesterday already that this lack of, when you work it out, the fact that the potentials really has this form means that this eigenlevel is actually lower than it would be for the real harmonic oscillator, and the amount by which it's decreased compared with the harmonic case is of order EC. That's the parameter that controls the anharmonicity. So the reason this has gone from EJ to EC because of the constants that I didn't write out here. So this is a useful representation, and I'm going to use this again for another case which is genuinely harmonic, and it'll be helpful notationally. I actually won't use this so much, but it gets used a lot in other analyses of the transmon. Okay, so I'm going to now immediately jump from the transmon itself to the setting of circuit QED, where I will use this. Now, I want to have a little bit of qualitative discussion about what we mean by circuit quantum electrodynamics. At one level, it's this circuit. So our job will be to analyze a little circuit, which will be like this, which I wrote already the last couple of times. So the QED is just to introduce other radiation fields. So this doesn't look like there's much other radiation fields, but it's all captured very minimally by this one little bit of the circuit. There's one mode of a radiation field. Now the actual setup, and I think it's important to appreciate the actual setup because there are aspects of it that you can't really capture with a discrete electric circuit, especially the discussion that I will be coming to about the measurement of the transmon, because I haven't told you how you would measure a transmon, and there really is a new modern method of measuring superconducting qubits, far superior to this washboard story that I told you yesterday. So now it's based on the fact that you can, in fact, make resonators for microwaves, for microwave photons, that have two different physical realizations presently. So there are things which are called, slightly dumb notation, but there are the 2D circuit QED and 3D circuit QED. 3D refers to, and you may have seen this, I believe, did Barbara Terhal show she showed some cavities yesterday, maybe. I don't know if she got to it even. So you can make, actually this is convenient, except it's too big. But in this so-called 3D technique, you take a block of aluminum, or a block of some superconductor, maybe a niobium, and well, you slice it in half, and then you hollow it out inside, and the hollow itself is some shape like the outer shape. So it would be some shape like this, except more regular. So rectangular, what is this called? Rectangular prism, right prism, and with three different aspect ratios. Three different length, width, and height being considerably different from one another. The reason to do that is that then it has a well-defined lowest mode of excitation. I mean, this has eigenmodes of the Maxwell's equations with conducting boundary conditions. And there's an eigenmode in which the electric field just points so along the sort of sandwich direction. So along the shortest direction, there's an eigenmode which just corresponds to the electric field lines pointing straight down from top to bottom. This is a mode at finite frequency, so the electric field vector is vibrating in that direction. So it's polarized. So its polarization vector is uniquely defined that way. There are higher lying modes where the electric field lines are twisted up in all sorts of interesting ways. But this lowest lying mode is like this. And then what's done is, so as I mentioned, this cavity is actually consists of two parts. It's two halves that are screwed together, basically. And you, I don't know if I can do justice to this here, but you suspend, you put a transmon onto a thin insulator, and you kind of suspend it from here. So here's this transmon sitting in space, in this plane. And so it's important, this polarization story is important, that the electric field is pointing this way. That is, the capacitor is here, and the electric field lines of the electromagnetic mode are this way. And that is sort of captured by this. Well, maybe it takes me a little longer to say why this this picture has anything to do with that. So this has a mode at some well-defined frequency, which I will, throughout today's lecture, call omega R for omega resonance. It has many more resonant modes, but they're all well separated in frequency. They're not, unlike, the rule for the where the other frequencies are is much simpler in the so-called 2D case. So maybe I'll mostly, in fact, concentrate on 2D, even though it turns out that this is the setting, and the multi-qubit versions of this setting, multi-cavity, multi-qubit, are the ones which have presently achieved the best coherence times. And the understanding of that is pretty simple, that I mentioned to you that there are some losses which you could represent as putting a high-value resistor here in the model, and that has to do with the presence of dielectric materials. And this structure is arranged so that it has minimal amount of dielectric material in the vicinity of the qubits. It's to the greatest extent possible just suspended in space in the midst of this cavity. That's not quite true. It has a very thin supporting membrane, but there's much less material. And so the capacitor, or the whole structure, is much less lossy in this simple classical way. And that has increased the coherence times. So the record, it's not that I've been saying these numbers very much, but the so-called T2 time, if you want, of this qubit, the qubit that's represented by this pair of states, has gotten up to some number like 150 microseconds. Now that doesn't necessarily mean very much. That's a pretty short time. But I should have said that the very first experiment that I featured, the first Cooper pair box experiments that succeeded in showing qubits that you could make a qubit in the Cooper pair box, had a coherence time of about 900 picoseconds, which therefore, of course, is 0.000, let's see, that's gotten me down to, is that the right number? I think that's right. 0.009 microseconds. So if I put all my zeros in the right place, this has been an incredible dramatic change in how these qubits function. Many orders of magnitude improvement of the functioning, so that you go from something which is barely a qubit. I mean, the vector on the Bloch sphere does a little rotation and it's dead. Whereas here, it's many thousands of rotations on the Bloch sphere are quite well accommodated. So this thing's really functioning nicely as a qubit. And I'll mention sort of what's happening. This implies certain things about the fidelity of quantum operations of 1 and 2 qubit gates. Maybe I could immediately say that as a consequence of this, more or less immediately, but I will say something about the actual mechanisms of doing this, that for 1 qubit gates, this has led to fidelities that are 99.99%. I think that's as far as they've gotten. But so really high fidelity single qubit gates. I think they wouldn't be so pessimistic about adding another 9 to this if it were absolutely insisted upon.
So what does the fidelity mean?
Okay. Well, I mean, I refer to say process fidelity of the gate. Does that mean anything to you? Okay. I think I'll assume I'm going to leave that behind because it's not my job, I would say, in this vast, impressive 2-week school to mention the ideas of quantum fidelities. Is it my job? Patrick is sort of scowling a little bit. Like.
No, I'm not scowling. I don't know that anyone else is going to do it. But
okay, we should have a copy of Nielsen and Schwang that we could sit here and then it could circulate around to people who needed to look up process fidelity.
Without defining it mathematically, you can say it's a measure of how well the gate works.
Yeah, right. I mean, okay, fair enough. I mean, a way of saying it. So let me amplify on that a little bit because it does more or less imply the following: that suppose you have some quantum gate, Hadamard or something like that, and that means some specific transformation on the Bloch sphere. And you could say the gates that we have are more or less the ideal gate followed by some n, some noise, which, there's some random number generator that you put in here. And so the random number generator applies stochastically some other operation in addition to the desired Hadamard. But it only does it, say, in this case, with 0.01% probability. That is, that much of the time this does not act. So that's one caricature of what the fidelity is. Because there's way more to it than that, because you actually like to know exactly in what way the gate is bad. Even at this level, it's informative to know that. And that I won't get into. I mean, there is a whole science of tomography, of gate tomography, that is well practiced, and practiced at a very sophisticated level, in fact, in this field, so that they know a lot more about the gate than merely quoting one number. Okay, but so enough said. I mean, here the fidelity might have been, 51% or something, but this is by a measure where 50% is sort of like a completely random gate. So it was really a pretty poor gate. Yeah.
So this fidelity, is it during the decoherence time?
Well, it's related to the decoherence time in the sense that if these diagrams you can associate, you don't have to, but you can think of them as connected to physical time, right? And then you can ask, how long does it take the gate to happen? Now, I haven't said that. Well, okay, obviously the gate has to do, in the case of Hadamard, it's, the Bloch vector's here, you apply some pulse. I am getting to that. And then the Bloch vector comes around, and there's a certain actual length of time that takes. Let's suppose it takes 10 nanoseconds. It's actually quite a plausible number in this setting. Now, now notice that this is 1/10 that time. So for sure, the Hadamard will not be executed very reliably if the coherence time is that. But if it's that, which is, okay, it's over to the other wall, then in fact very little decoherence will occur during this interval of time, during this short interval of time. So it makes it possible to achieve this, but it doesn't guarantee that you will achieve it, because there are other ways that gates can go wrong other than decoherence. You can have bad quantum control, or you can have, the control itself can be noisy, or you can have leakage. Okay, who doesn't know what leakage means? Oh no. Okay, well, I guess I just have to say that leakage is a technical term in quantum information that refers to the fact that often the physical object that you want to use to embody a 0 and a 1 has more quantum levels. That's not always the case. A spin 1/2, the Hilbert space, the spin Hilbert space of a spin 1/2 particle is in a native way two-dimensional. So there's no possibility of leakage in the spin Hilbert space of an electron. But for the eigen-Hilbert space of a transmon, there's plenty of chance for leakage. So here's a label, a state which I can perfectly well label 2. But if I'm doing a 2-level quantum logic, I'm using qubits, and I have some evolution that gets me partially into the 2-level, that's also bad. That also is contributing to a loss of this fidelity. But it behaves rather differently. That's where this caricature is wrong, in fact. Unless I allow this noise operator to be explicitly something that takes me up into higher levels. But then, it does matter a lot when you get to quantum error correction, that the means by which you correct leakage error going up into these levels is quite different from the way that you correct regular decoherence, let's say.
What's the reason of a TR?
Pardon me?
T2. What's the reason of a T2 improvement? T2.
What is the T2, or what?
The reason of a T2 improvement.
Oh, why did it improve? Very many small reasons. There's no really fundamental reason why it improved. You don't even see it in my model. Well, you've seen it in a few places in my model, in the sense that if I just draw this, T2 is infinity, and there's no concerns. But so first of all, there are these resistors. So the presence of these resistors has been more and more rigorously excluded. So that's one thing that's contributed to the growth of T2. It just means T1 has gotten longer also. These other kind of noise sources that I refer to as sort of classical, like time variation of offset charges. As I mentioned last time, the Cooper pair box is very sensitive to time variations or noise of the offset charge. And then in fact, that was a large contributor to this. Another contributor is that initially the measurement apparatus, the thing that was in the experiment to measure 0 and 1, was itself very invasive, so that it made the system open, so it made the T2s intrinsically short. So now we have much less invasive measurements, some things that are much closer to ideal non-demolition measurements, in fact, so that they do not, you can really turn them off, and so that they do not influence T2. So that's a short list, but there's a rather longer list, in fact, of things that are a combination of better design of qubits, better design of the experiments. I have to say that the experiments have gotten very complex. Experiments to me are always complex, but the schematics of the experiment are very complex because of they have a lot of filtering and very careful design of the amplifiers, and in other talks that I give, I begin with such a circuit schematic, and you see something where there's a qubit down here in the schematic, and then the schematic is filled with things, with mixers and filters and amplifiers and things like that, and circulators, and here's another amplifier, and you're very careful about that amplifier. So the whole page is filled with pictures like that, and the refrigeration is in stages here. So there's great deal of sophistication in experimental physics in very much protecting this qubit. All of this stuff is meant to protect the qubit from noise, but also make it accessible to accurate measurement. So, sorry, that's very schematic. So, but thank you for the question.
Another question. If you put the qubit into the cavity, the electric field is influenced by the qubit.
That's true, somewhat. So I've, in fact, and that has been the subject of recent research. It doesn't change the principles very much. I mean, I just said, yes, this mode has a perfectly polarized electric field. Indeed, that's not true. There is some distortion of the field due to the presence of this qubit, the metal of the qubit. I'd say that's a sort of uninteresting renormalization. I mean, that's a sort of fancy way of saying it. It just changes the electromagnetics a little bit, but it doesn't change the fact that there is a resonant mode. And you can even predict how it's shifted by these distorting effects.
I know there are some situations ultra-strong coupling.
I'm sorry, ground couplings?
Strong
coupling.
Strong coupling. Strong coupling. Okay, yeah, strong coupling is not the same as strong distortion of these fields. Although maybe there's some relation between them. They're usually thought of as apart. I actually will avoid, I mean, there's a whole science of strong and ultra-strong coupling, which involves some symbols that I haven't written yet, which I will generally avoid in the sense that if your objective is to make nice quantum circuits, it's actually, there doesn't seem to be any real use to the ultra-strong coupling regime. The sort of moderate coupling regime, what was always called the strong coupling regime, but just regular strong without any extra ultra or super or whatever strong, is perfectly good enough for what's going to be done here. Okay, now I'm again getting to my digressive mode, so I have to. I should be more linear here. Linear thinking. Well, we'll see. Well, I hope I get to the whole story. So I explained 3D. Let me just briefly explain 2D. So 2D is based on doing things on chips. So everything will happen on a chip surface. And so what is used is a technology. Remember, we make these planes of metal. So here's another thing you can do with planes of metal. Sorry, this is... see if we can find a slightly better one here. You can make strips of metal, but now I'm at a somewhat different scale than I have been generally. And I'm going to have a hard time drawing this to scale because the dimensions are rather disparate. So there'll be, this is one basic motif where you have a long stripe of metal, this is thin film metal, with some gaps, so insulating or just nothing there, and then strips of metal somewhat wider, and I mean often actually infinitely wide or much, much wider. It doesn't actually matter how wide it is. So this is, well, a few things to say about this. This is a transmission line. So it's also, if you took a regular coaxial cable and you cut it in half and you looked at the profile of the metal, that's what it would look like if you did the cutting carefully enough, because it has an inner conductor and then a circular region or an annular region without anything, and then a shield, an outer shield of conductor. So this is a transmission line, and it can work. Actually, transmission lines of this form are intrinsically broadband, so they'll carry radiation at almost any frequency, but it's chosen so that it will very conveniently carry radiation in this range of frequencies that I've been talking about, some number of gigahertz. Just more or less like your coaxes for your television carry. So you can have these go on forever, or what you can do is occasionally interrupt them. So here's something, and this is actually a gap, and this is actually a gap. So you just leave out, or in your metallization, the lithography, you just leave out a space there. So that's enough to make a cavity. And despite the name 2D, this is really a 1D cavity, in the sense that it's just the just the modes of or the wave modes, electromagnetic waves of a single one-dimensional line with boundary conditions. I mean, the boundary conditions now set by this. But if this gap were very, very large, then this would just be a really isolated cavity. And in fact, but it's important that there actually is still some capacitance from here. And this is completely analogous to, not sure how I want to draw it, but a regular cavity QED. So those of you who work in that field, you're familiar with these sort of mirror cavities, but now for optical wavelengths, not for microwave wavelengths, where there's some electromagnetic field which sort of mostly lives here, but then this mirror has some reflectivity which is like only 99% or something, so that if you send radiation in from outside, it is capable of going in, and conversely, if there is radiation in here, it can actually get out. But that it is pretty nearly an isolated cavity. So there's a well-defined resonant mode at at frequencies determined, or at frequencies determined by the geometry of this. So so this has some omega r. It actually, of course, it also has a simple progression of higher harmonics. 2 omega r, 3 omega r. We won't worry about them for this discussion. Just to give you a sense of physical scales, this is now actually on the scale of a few centimeters. And that permits, so the lowest lying mode, which has a wavelength or half wavelength of size, is what corresponds to this microwave frequency, so to gigahertz frequencies. And then, yeah.
Metal wires, or?
They're thin films of metal that are evaporated onto a chip. On a flat plane. So obviously you can see them, so it's not microscopic anymore. Nevertheless, this will be highly quantum mechanical, but it's on a two-dimensional plane, right?
Then cavity is one-dimensional.
Well, sorry, what I should have said, this is not to scale in the sense that this is maybe 10 micrometers. So what this actually looks like is this. It looks like something very long and thin. If I do the horizontal and vertical to scale, but I wanted to do it intentionally not to scale to show what else happens here. I did want to make one point about this. So this is some centimeters long, but it's also perfectly fine to do this, and it's usually done this way, that the line can meander. And that actually doesn't change the electromagnetics very much. As long as the bending radius is larger than this 10 micrometers, then it still functions as a one-dimensional cavity, even though you've wrapped it up. It's important that it's wrapped up in such a way. There's still mostly a lot of this quote outer conductor, this outer conductor, inner conductor. There should be a lot of outer conductor in between these two parts of the meander. Okay, now this is the cavity. This is indeed the realization of this part. And I've actually gone back to look. This is about 40-year-old, you might say, technology or technique. Yeah.
Why is it only on 2D plane, then the radiation doesn't go out of the tank?
Oh, yeah, okay, well, that's a good question. Well, it just turns out it doesn't. It is, even in this geometry, the radiation is confined. So if you look at a cross-section, here's this thin metal, and then a gap, and then the thin metal on the sides, and you look at the, so I claim there is, in fact, traveling radiation and guided radiation, confined radiation that goes this way, and the electric fields look something like this, of that mode. So it has no simple linear polarization, but it does have a strong concentration of the electric field pattern, inside this gap, and with really only evanescent, only quite weak fields out here. And so, yeah, indeed, although I haven't really thought that through completely, it probably has also to do with the the width of these ground planes. If these are not infinitely wide, then there is some leakage out to free space. But that is never even discussed. So I believe for these geometries, that leakage out to free space is really negligible. It's been told to me that when these metals are superconductors, that the quality of this as a waveguide, as a way of guiding radiation, happens to have basically exactly the same characteristics as optical fibers in the infrared. That is, there's some loss. So the loss per distance is some number like 0.1 decibel per kilometer. So in other words, it's these things where you can actually go hundreds of kilometers and still have a usable signal. Now, nobody has refrigerators that are hundreds of kilometers long, so nobody actually uses it in that mode. But over the, the meter or so, well, it never travels a meter. Over the quite a few centimeters that it travels on a chip, that free space loss is really negligible. I was going to comment that since this is centimeter scale, you can actually see it. If you're invited into a laboratory and they say, here's our quote qubit. Now it's even looser to say because it's not the qubit you're seeing, but it's the cavity. So you can actually see it. The trouble is the contrast is not very good because these are thin films. So you catch it in the light and it's a shiny piece of silicon or something, and then a slightly different shininess you can see of these things. And of course they're very thin, so it's like seeing a hair on a not very good contrast surface, but it's quite visible. And if you really squint, you can even see the transmon. Now, I haven't put the transmon there yet, but let's put it there. Actually, I'm going to conform to the practice that's almost universally done in papers on this subject, which is to do colors, which are, of course, completely fake. But to emphasize what part is serving what function, you colorize the photographs. But it's all the same metal. So the transmon just sits right in here. And so what mostly is present is capacitor. Remember, I've emphasized the transmon is made to have a pretty big capacitance. And then in here, which you really can't see, is some very, very tiny bridge between these two pieces of pink metal. It's all aluminum. And then in here is some crossing thing, is some Josephson junction. So that's really on some microscopic, some completely invisible scale on this, in this. Of course, I'm using some false scales anyway. I can put an X in here just as a reminder that, yes, there is, in fact, a Josephson junction there. But mostly there's capacitance here. But the point of this, and it connects to this picture as well, that the eigenmode of radiation of this is coupled, and that's where it can, in fact, without too much difficulty, be very, very strongly coupled to this transmon. And it is because of the fact that the electric fields are pointing this way of this traveling mode, or, well, the standing wave mode, I should say. So that's the origin of, what it really means, if you can actually more closely have it correspond to this model if I put a capacitor here also. And here they are. There's a capacitor from here to here. Let's say this one. And then here's the transmon. So it has a capacitor and a Josephson junction in parallel. And then another capacitor coupling it to the bottom. And then this is the resonator. So this is a resonator. It's an LC circuit in this model with only one resonant frequency. So I'm only representing by that one of this. And those are, of course, hard to identify. There is not a discrete capacitor and a discrete inductor that I can identify. You can, I'll get to you in a moment. You can use, let's see if I use this, use a slightly different drawing of this. There is a standard model for a transmission line, which is an array of inductors and capacitors like this. So you can make this model more, quote, accurate by adopting that and then you have a pretty good physical model of the actual, electromagnetics of this. But it's not necessary to model one mode. Question?
Yeah, you covered this, the first one, only with one capacitor in the beginning. So could you actually just leave one half of the transmon capacitor to the outer conductor?
Yes, it would be permissible. There'd be no real problem with just having these, as we say, galvanically connected, really the same. There's not really any problem with that. I don't even know why there's. I don't know why it's really done that way, frankly. Sometimes these are chosen to be different metals, because since this metal doesn't need to have any Josephson junctions, you can use a variety of other superconductors for that. But this, since it ultimately has to connect to a Josephson junction, should somewhere be aluminum, because aluminum is the one and only sort of premier metal for making a Josephson junction. And the reason why there's no real need to do it either, I mean, if you go into the formal circuit theory that I was discussing, you're allowed to use usual simplification rules of electric circuits. And, this is in series with this, is in series with this, but, you can commute things in electric circuits. So you could put this capacitor up here, and then there's simple, series combination rules. So it says you really don't need this in the model. And if you put it in, you find that you have sort of a degenerate degree of freedom that you should eliminate anyway. Okay. All right, so that's the schematics. Now let me write down, actually in pretty short order, the models that describe this. And the model is really just simply the circuit analysis of this circuit that I've been discussing. So this is a circuit. I'll just make a little bit of contact with what I've been saying before. This is a 3-node circuit. So this is the graph theory of it. And it has a spanning tree, which can be taken just to be these two capacitors. And so it should have, and it does in fact have two canonical coordinates when you write the Hamiltonian. And let's write it. Put it here. Okay, so Hamiltonian. And it's partly going to be what I just wrote. I'll temporarily write some of the same symbols. So first I write the terms coming from the transmon, 4EC, Q minus Q offset. But here I'm going to, in fact, do what was caught at the very beginning. And I'm going to do a little bit of a shorthand derivation. I mean, there is actually a real C number offset, but here it has a kind of Q number offset. I'll explain what I mean by that in a moment, because this is seeing a voltage from over here. This will actually have a name here, VR. But that's an operator, so that's going to get me through this derivation pretty quickly. So minus EJ cos phi, and then plus, I need terms for these two elements, but these are just linear circuit elements. So now I'll go back to capital Q for this capital Q sub R squared over 2CR plus phi R squared over, is there a 2? Yeah, 2LR. So these are just the two canonical coordinates. I guess now I've written it, more with reference to the invoking the idea of a flux through this inductor. But as I've discussed, it doesn't really matter which I adopt. So this is just the Hamiltonian of an isolated LC circuit, just a harmonic oscillator, and I will straight away rewrite those in creation and annihilation operators. And then I have the Hamiltonian of the transmon, and what's not shown, but it is actually here, is the fact that there's a coupling term. This is just a sort of shorthand way of writing it, or a convenient mnemonic actually, because it connects this idea of offset charge with the possibility of coupling to another circuit, because it turns out that this Q offset as an operator is, where do I have it written here, is CG. Sorry, now I can really write CG. I should have also written CR, C for the resonator, L for the resonator, what else? The EC and EJ are for the things just about the transmon. So this is, well, it involves the factor CG over twice the electric charge times VR. Now, VR, but again, an operator VR. But what do I mean by operator VR? VR as an operator, I will make sort of by definition. These are all, in a sense, definitions, because I'm not actually giving you the derivation, but only the result of the derivation. The VR is 1 over CR QR. Good. So that QR, we know what that is. So that's actually just a statement of the coupling Hamiltonian. So, and I see coupling by squaring out this term. So it's the cross term that is the thing that gives me the coupling. The square of the Q offset just gives me a little extra contribution to QR squared. So I'm actually not even going to keep track of that. Okay, but let me go through a few more lines of derivation. So let's keep the, okay, we have 4EC Q squared. I'm not going to change that for the moment. And this minus EJC cos phi, that's coming along for the ride. But then I'm going to write the following. I'm going to write omega r a dagger a plus a half. That's this pair of terms rewritten in second quantization. So I've introduced creation operator a, or a dagger, for that. And omega r here, I'll put it here, omega r is equal to 1 over the square root of L sub r C sub r. It's just the usual expression for the resonant frequency of an LC circuit.
Why do you call the second quantization?
Why do I call what?
Second quantization.
I still didn't catch you, sorry.
You call it second quantization.
Oh, second quantization, or Dirac notation. Why do I call it that? That's what they always taught me to call it. It's just indeed another basis of operators. It makes more clear, or it emphasizes the fact that the Hilbert space is a Fock Hilbert space, where the quantum number in the harmonic oscillator becomes the important focus. Okay, so we get that, but I haven't rewritten the coupling terms. Well, the coupling terms turn out to be minus 8EC Q times Q Q offset. And now let me just develop that operator a bit. Just see where do I actually go with this. Okay, I actually do two things, and unfortunately I don't see a write-up of the. It would be nice to keep track of these parameter values, but I didn't do it all the way through here. Let's see. So we'll get rid of this 1D cavity or 2D cavity picture. Right. Okay, sorry. So I will just take these terms and, well, I will note that this, Q times Q offset. This Q offset is proportional to QR, and QR is in turn proportional to I times A minus A dagger. So that's actually a sort of important step that I wanted to show you, that's going to get us to a rather standard-looking atom-cavity interaction. I mean, we're very close to a Jaynes-Cummings model, basically. I just have a few more steps to take to get us to that point. Because the only further thing I want to do, let's see, do I still have it written here, is to for the qubit, for the transmon, not for the oscillator, but for the transmon, to immediately restrict the model to 0 and 1, just for simplicity. In fact, you wouldn't really do this if you're doing serious theoretical work to analyze this. But for pedagogical purposes, let's go to just reduce the qubit, reduce this to a single qubit Hilbert space. Because then what I would write is that, I guess I'll write it straight away here. So the H of the transmon plus cavity in this qubit reduction, or reduced to qubits, is equal to, so we have this omega r a dagger a. Well, I have this 1/2. I'll keep with it, although that's kind of dumb to keep writing it. So it's the harmonic oscillator. It's plus, and now I use I. This is now going to be this term I, and now I have a new parameter g, a minus a dagger, and now I have this q term. That's a position operator of the harmonic oscillator. The q is this coordinate. Perhaps, well, can you believe me that if I restrict myself to this space, this operator becomes just the x, the Pauli operator x? It's something not diagonal, indeed, in this basis. It's related to the fact that it's a plus a dagger, so it's something, it's an operator that causes transitions between the 0 and the 1. So I will straight away write x here. Everybody okay with that? I mean, I've suddenly transited to quantum info notation. So I mean, a real solid-state physicist would never write this. They'd at least just write sigma x. And then we only have to account for the qubit itself, and the qubit has some, well, we don't really have a drawing of that, but if this were the qubit, I guess it was the qubit in this, there was some energy difference between 0 and 1, which I could call omega q. And so I need finally a term omega q z over 2. Just diagonal, using the diagonal Pauli operator. So that's the that's really the sort of working Hamiltonian, the one which you use to think through a lot of the effects for this qubit cavity combination. And it is, in fact, indeed, I think without any modification, it is exactly the Jaynes-Cummings model of quantum optics. Well, there's one step that I think we will take in a moment, which is to slightly reduce this term. Because what we haven't done, I guess Jaynes-Cummings would normally involve so-called rotating wave approximation, which we haven't made yet. I'm not going to really derive this. I'm just mentioning these things. That this term is, so it's a minus a dagger. Now x I write as, now I go back to another notation, sigma plus sigma minus. Sigma plus and sigma minus are the sort of raising operators, raising and lowering operators for the single qubit. So sigma plus is something like that, right? And sigma minus is its Hermitian conjugate. And then you argue that if you expand this out, that you get 4 terms, of course, and 2 of them you argue away within a rotating wave approximation. I won't go through that, but hopefully it's familiar to many of you at least. But I want to use this as the basis for some further discussion, because now this actually gets me to a point where you can quite effectively and rapidly talk about a whole bunch of things. How do you really do 1-qubit gates? How do you actually do measurement finally? So the rotating wave version of this will reduce this to a term g times a dagger sigma minus. I have a plus here, so there's been some change of notation, some change of convention, plus a sigma plus. sorry for this sign change. This is not good. But, I've gone from the September 18th notes to the September 25th notes, and somewhere that sign got lost. But that sign is not so significant. It can be reabsorbed in definitions. Now, this G is, that's a traditional notation for an atom cavity coupling. You can see that it was, in fact, it was proportional to this coupling capacitance. So the way you make G bigger or smaller is by changing the geometry of the thing that I just erased, of just having the capacitor, the transmission line metal and the transmon metal closer away or further away will affect that. It's just simple geometry. And it can, in fact, be put into regimes that are very, very nice for qubit behavior. In particular, this sort of strong coupling regime is quite easy to achieve. Strong coupling just means that the Hamiltonian, the effects of this Hamiltonian, in particular, the gaps that are going to be produced by G, which I'll sketch in a moment, are larger than any of the decay channels of the cavity, leaking out of the mirrors or leaking out into free space. That's easily achieved. So that's strong coupling in the point of view of optics. Yeah.
I've got a question about the derivation. You absorb the Q offset term into the omega r, essentially.
You mean the Q offset squared?
Does this significantly change the frequency?
No, not significantly. It's a small renormalization of that frequency, and it obviously doesn't change its operator character at all.
Yeah.
So it's just absorbable in a slight change of this resonator frequency. The resonator does indeed get loaded by the transmon, so it doesn't have the classic, half wavelength frequency that you would expect for the bare cavity. But it really doesn't affect any physics, and it is numerically pretty small. So I can mention a couple of numbers that this G, we're in this setting where omega Q and omega R will be something close to my magic 5 gigahertz, although it will be actually relevant. There will be cases where I don't want them to be equal. And the G is very readily settable in a range which is something in the range of hundreds of, let's say, 400 megahertz. It can be made bigger, and this ultra-strong physics happens when G is comparable to these frequencies. That would be kind of ridiculous for regular optics, because G would have to be hundreds of terahertz. I mean, it just doesn't happen. Atom cavity couplings cannot be, and in regular optics, cannot be anywhere close to the radiation frequency. But here the radiation frequency is way, way lower by 5 orders of magnitude than in ordinary cavity QED. And the couplings are, if anything, larger. These are sort of atoms with the big dipole moment, because they're really physically big. So they kind of naturally have bigger couplings to radiation fields than regular atoms. Maybe for Rydberg atoms, it's not so different. In fact, these are a little bit more similar to Rydberg atoms in this cavity coupling physics. Okay, so let's do a few things that you can do with this basically right away. Just seeing if I have it written well enough to just say it. I think I can say it just based on this. So one thing you can do, and this is where it gets awkward to say what this means in the circuit model, is you can, I should have saved my 2D circuit because I am actually going to redraw it basically again. So remember, you have this transmission line. I'm going to be more schematic. The transmon is here, and it's coupled capacitively to the outside world. There's the same thing, by the way, with these 3D boxes. You have these boxes, but in fact you drill holes in them and you insert a coaxial cable into the interior of it. So that's the equivalent kind of capacitive coupling in that case. So we're going to now set up this toolkit for how you really manipulate this transmon. And the first thing is we'll send in, remember we have omega q and omega r, there's omega q for the qubit, omega r for the resonator. Let's suppose these are not the same. Let's suppose omega r minus omega q is, well, for example, a lot bigger than g. What happens if I send in radiation at omega q? Now, this under these circumstances, and when I say send in radiation, I'm going to be talking about a coherent state. Coherent state, do I need to say, okay, if I say coherent state as an optical field, are people uncomfortable with that? Do people know what I mean by that?
Barbara mentioned it yesterday.
Okay, that's good. So, because indeed it's not an eigenstate. You know, if I think of the field as one harmonic mode, one bosonic mode, it's not any particular photon number, but it's a specific, linear combination of photon numbers with maximally classical behavior. So we send in a coherent state. Well, for this lecture, we do completely coherent states. It's actually fun to do some squeeze states, but that's a more advanced subject. Okay, I send in this coherent state. What happens? It gets reflected back almost completely because it's mismatched. I mean, it's not in resonance with this. That's just standard cavity, a fact about cavities. If you have a cavity, there's a concept of a cavity line width, which is basically this G, and if you're far outside that line width, then you reflect. But not quite. You actually can get a little bit of excitation of the cavity field at this wrong frequency. So, and that's really what is done to do 1 qubit gates. So you waste a lot of this radiation, but microwave photons are really cheap. So you can in fact send in high intensity, well, quote, high intensity. It's still kind of trivial intensities from the point of view of a microwave generator. You know, your microwave oven is producing such gigantic numbers of photons you don't even want to think about it. But so you send in, you turn on your microwave oven and it sends, or somewhat better version of that, of the magnetron, and it sends this radiation here. Almost all of it gets kicked back to you. You absorb it into something, or you make sure it doesn't multiply reflect. That's part of the reason for all these wires and filters and stuff, that managing the reflected stuff, making sure it doesn't heat up things too badly when it goes back. But a little bit still goes through. And so it's permitted to talk about a coherent state will have a finite expectation value of this. So we replace this by an expectation value of A minus A dagger. And this is some finite number. This is sort of like an electric field. And I can also shape it. I can turn it on and off, basically. Well, that's sort of textbook. If you had Nielsen and Chuang sitting here, we could all pass it around and remind ourselves that that's a completely standard scenario for doing 1 qubit gates. That excitation will do a nice rotation on the Bloch sphere of this single qubit, and that's indeed the thing that's getting us the 99.99% fidelity. I guess a few comments. I talked about it. It looks like only an X coupling, but you can merely by changing the phase. Let's see. Let me find some color here. So I sent in some pulse. Carefully sketched, of course. But if I'd sent in radiation like this, differently phased, that's not so well chosen because the distinction is supposed to be between cosine omega qt versus sine omega qt. This is so-called in phase and out of phase. Sine omega qt. In phase and out of phase, that turns this from an X to a Y, it turns out. So you can rotate anywhere you want around the, I'm imagining a Bloch sphere. I want to rotate this way, but I can also rotate that way, merely by rephasing this radiation. That has to do with the fact that it's most natural to think of this qubit in a rotating frame of reference. And so this change of this radiation phase is just going around the azimuth of the Bloch sphere. So that's
that term is absent, or coherent wave will be reflected.
the coherent wave, as I say, will mostly be reflected. We're using just a small amount of it that still is transmitted.
Due to that additional term, or
Due to what? Sorry.
that small amount of absorption due to that interaction term, or
No, let's think about that. No, it is not. Oh, yeah, I should have. Sorry. No, I did something wrong, which was indeed confusing. I mean, wrong only. Some of my words were wrong, and this symbol was wrong. Sorry. Because, well, it was right, but I need something else as well. This is not the line width. This is where I'm outside the circuit model. This G has to do indeed with the coupling between the qubit and the field. There's another parameter which is usually called kappa. So there's another coupling capacitor, you might say. Well, it is a capacitor that relates this. So it's this kappa that relates, which is proportional to the capacitance here, that tells us how much of this is whether or how much of the radiation is transmitted into the cavity. It also tells us if there is radiation in the cavity, how long does it take to leak out. So G is in fact also much bigger than kappa, or bigger than. This is in fact what's called strong coupling, because this kappa counts as a loss from the point of view. This is no longer a closed quantum system once kappa is non-zero. But it's small enough that it can be small compared with all these other parameters, but its being non-zero is enough to let radiation in and allow 1 qubit gates to be performed.
definition of a coherent state in here is based on the state annihilated by a operator, not really.
Well, an eigenstate of the A operator.
Not based on the real vacuum states of whole system, because due to that additional term a minus a dagger,
Mm-hmm.
vacuum state of this Hamiltonian will be different from the state which a annihilated, which is like a different vacuum state. Because if you put the interaction term,
Yeah.
you will have
You mean this interaction term?
yes, some sort of interaction term that, for example, that interaction term. So that due to that interaction term, harmonic oscillator vacuum state is different from the vacuum state of that Hamiltonian.
That's true.
So coherent state is defined based on the harmonic oscillator,
Yeah.
not the real vacuum and first excited, second excited state. That's why.
Well, Okay, you're getting into potentially, a potentially extensive discussion, which I'd like to shorten by invoking the idea that I could have come at this in a more direct means. That is, I say, this is a signal with an electric field, and the coherent state is a way of saying that it's a quantum state, but it has a very well-defined. It's a high-intensity state, and it has a large electric field. Its intensity is strongly diminished here, but it's still strong. It's still a many-photon state. So it's still far from vacuum, and it still has a classical expectation value of the electric field. And so I'm allowed to, without too much error, to replace this by a C number in that setting. So I will not, I can avoid talking about the quantum character of this under these conditions, when I've strongly driven the cavity. I will be doing other things in a moment where I don't strongly drive the cavity, and I actually do care about the quantum nature of this term. So this term does play several different roles in this discussion. Good. Okay, but so we finally did after 3 lectures, I finally got to a real legitimate and actually highly accurate quantum gate. So let's do a little bit more. Let's do measurement. But to do measurement, I want to use this condition a little bit further, because this condition, so this condition was strong coupling. This condition is what's called the dispersive regime. And I have to explain what that means. And I wanted to use a picture to kind of convey the concept of that. But now let's see if I can find my picture. I found my picture. Okay. Because I'm actually going to have to get back to, we're getting back to sort of eigenlevel repulsion, so another kind of ubiquitous subject here. And I'm going to derive in pictures something that I would do by some formal perturbation theory based on this. Whereas I say I really formally treat this as a perturbation term and derive a different effective Hamiltonian. But as I say, let me get at it pictorially. I will use this board. Because let's just again pretending that the transmon is a two-level system, we're going to actually just draw a picture of the eigenlevels of this joint system, of this single cavity plus qubit system. So what I'm drawing here is omega q. So I'm just imagining, I'm going to just consider a situation where I imagine omega q as a tunable parameter. And, well, we will have a physics situation where it's a tunable parameter as well. But it's, at the moment, just just for an exploration of the mathematics. And this will be the energy, or the eigenenergy, eigenenergies of the system. And I'll do it so by definition, this line, 0, is really the state 0, 0. So the qubit is in the state 0. I want to make sure which one do I mean. Yeah, qubit is in the state 0, and the harmonic oscillator is in its vacuum state. Now, a lot of the story is just this, that, well, if G were 0, this would already be most of the spectrum. So there's something, this is at omega r, twice omega r, 3 times omega r, etc. So these are the levels of filling the resonator with successively larger numbers of photons. I don't need that many for this discussion. And now I have, to complete this, again, if G is 0, this would really complete the whole story. I just draw lines like this. And that's well enough drawn. These are supposed to be lined up, so that's a flaw of this drawing. But so this is, I can label this 1, 0. So this branch is just the state where there's, we're in the excited state of the qubit, so we're higher by omega q, so these are really 45-degree lines. And the resonator has no photons. This is 1, 1, this is 1, 2, 1, 3, etc. Now, something else happens at these points, and it is a pity I didn't line them up. I'm wondering whether I should bother. Okay, I only need about this much of it, and these are lined up pretty well. So G is non-zero. So, and that breaks this quantum, I mean, these are not good quantum numbers then. And in fact, here, these levels repel. So actually what happens here is that these separate, and if I'm not mistaken, the gap is 2G. Here there's a gap, and what's very important, in fact, is that it's larger. It's, again, if I'm not mistaken, but I didn't write it down on my notes, I believe it's twice times the square root of 2G. Yes, I'm pretty sure that's right. And it's square root of 3, square root of 4, etc. So the gaps widen as you go upward. That's just a fact about diagonalizing this Hamiltonian, which in the rotating wave approximation is actually very simple. It just decomposes into 2 by 2 diagonalizations. So no hard work involved in getting that. But I just want to consider, well, I'm going to motivate a term which I know you've seen already. So I'm going to claim there's, let's see, that there's a new term that if I work in a dispersive point, now this point is not the dispersive point. This is sort of the resonant point. And it's also the point where you get vacuum-Rabi effects, just again to give you some other words to remember, vacuum-Rabi. You get these are called vacuum-Rabi splittings. But I want to work away from those. So let's work, say, here. This is a good place to discuss the dispersive approximation. So I ask, if I'm in the, let's ask the question this way. Suppose I'm in the one state of the qubit. Then what does the frequency of the resonator look like? So I'm in the one state. So I'm in the one state, and here's the, quote, vacuum state then, a vacuum state of the resonator. And then here's the one photon state and the two photon state. Because of the growth of these gaps, this interval is a little bit smaller than omega r. So in fact, and that's true all the way up here. So it actually looks like the resonator, if you've set the qubit to 1 and you say, what's happened to the resonator, it's gotten a little bit lower frequency as a result. And so that motivates, without deriving, the fact that in the dispersive approximation, in this dispersive regime, you can use a simpler version of this Hamiltonian where this term is replaced by, I should have left some space there, but so the interaction term becomes, rather than a dagger plus a x, it goes to a dagger a z. Left some space for some constants here. But now this is just said in symbols what I just said in words. That is, this is a term that adds to, remember, of course, there's this term that just tells me the frequency of the resonator. But now there's a new term that also is a dagger a, but it's dependent on z. So if z counts whether I'm in the upper or the lower state of the qubit. So it says there's a shift of the resonant frequency dependent upon the qubit state. And that's as much of a derivation as I'll give today. And the prefactor is g squared divided by this difference. Well, it's omega r minus omega q. And have I got the sign right? I'm not sure. I think I don't, so I'll put a minus sign here. But that's sort of provisional at this instant. So it says that this is well known about Jaynes Cummings. I'm not actually, those of you who do quantum optics, you've already seen this in studies. If you're working dispersive, then it's much more convenient to use this as the effective Hamiltonian. And this is really nice because this is non-demolition, or will be. That is, things that happen to the radiation field interact in non-demolition fashion with the qubit. So the qubit part of this interaction Hamiltonian commutes with the qubit Hamiltonian, with the system Hamiltonian. So it's the usual criterion for non-demolition. And so we're immediately going to use this to measure the qubit. So
something in addition there to change the x to a z. I mean, effectively conjugate.
yeah, that's true. Yeah. Well, remember, notice there's a g squared here, and well, yeah, the operator character does change. Yes, as a result of this perturbation theory.
But I mean, since you effectively conjugated by a Hadamard on that term, you have to do it on the other term as well.
No, it's not. Let's see if I can think of what to say about that. It's confusing to write x because it's really based on the already on rotating waves, so I don't have x's anymore. And I get products of these operators, and they manage to end up giving me z's. That's where I just don't have this derivation at my hand at the moment. But I'm certain of the result. Let me put it that way.
Looking at
Yeah, of course, this is only approximately non-demolition, I'll say. But indeed, the leading order term that you get in perturbation theory is in fact Z. Sorry to just do this by assertion, but I'm getting a little tired, so I couldn't possibly get my mind to do this derivation at this instant. Okay, but good. Okay, so now we're going to measure. So finally, I get to how the sort of modern method of measuring qubits, much better than these things of blasting the system or heating it way up and doing something destructive to it. Because here, oh great, I didn't erase this. I didn't know if I had or had not. So the way I measure is to do the same kind of thing I did for single qubit gate, except I just have to relabel this omega r, or almost omega r, because what's omega r now? And I'm in this dispersive regime. So I shine in a tone. Turns out its phase won't matter in this case. And so let's see what happens to this tone. It's now basically in resonance with this, so it actually mostly goes right in without a lot of reflection. Well, it's in. This is sort of stupid because the wavelength is in fact the cavity size, so I'm not really doing a good cartoon of that. But you energize the cavity. You put a lot of field in the cavity, but all you're supposed to think about, okay, I just have to now state a couple of other facts. This is non-demolition, and it's going to be a measurement. So I'm allowed to just think through separately what happens for the Z being in the -1 versus 1. That is, you just have to study what this experiment does for those two different cases. And for those two different cases, there's nothing left here. It's just a pure linear optics problem. But with a omega r, so the actual new omega r, the omega r including the qubit state, let's see, how do I want to say it? Yeah, I'll call it B for bit. You're trying to learn the bit, which is a qubit. That is omega r plus, minus or plus -1 to the b. So it's a plus or minus 1, depending on whether b is plus or minus 1. And then it's this dispersive shift, which is just a number. It's actually usually called chi, just to save some symbols. This combination is called chi in this business. So it's either red shifted or blue shifted. So it means that if you shine radiation in at the original frequency, it's not quite in resonance with either. But then what you have to know are just some things about linear optics. It's just totally a fact about classical linear optics of what happens to a tone if you shine it through a resonator and it's not quite on resonance. So here's the story that you look at the transmission coefficient as a function of frequency, and you look at the phase versus frequency. That means the phase of, we're doing transmission, so there's an outgoing field. It will do stuff here, and it will transmit through, but the phase of this classical coherent state does interesting things as you vary the input frequency. Now, the transmission does something like this, and in fact, it hits 1 at omega r. Well, sorry, but this would be, I'll put some color on here in a moment to emphasize what happens. This is the empty cavity, no transmon. You would just see this. And you have a phase which evolves from 2 pi to minus, no, sorry, from pi to minus pi as you pass through here. Now, but that's the empty cavity. Now we have the filled cavity, and now if you're 0, then it's down here somewhere. And the phase change is also like that. It's shifted over because it's shifted over to this modified. This is omega r0. And then if the qubit is 1, it's over here. So this is omega r1. And with a corresponding phase shift over like that. Now that's perhaps an exaggeration of magnitude. But anyway, what is typically done, now you have a real distinguishable field. If you shine in a tone here, it's not distinguishable in its amplitude. There's still a certain diminished amplitude that's transmitted, but it's wildly distinguishable in its phase. So So you usually do some interference, some homodyne or something measurement of this field, and you just detect what phase has emerged. And that has done the measurement. That's done the collapse, etc. And that's quite an effective measurement. And effective also in that it really has not done very much to the qubit. That is, when you turn off the tones, the qubit is nicely in the state that is indicated by the measurement. And very little extra energy has been deposited in the system as a result of doing this experiment. It's left no trace, except that it's, however, collapsed the qubit into the state. So that's the method of this dispersive method of measurement, which is always used now in this. Now, can you remind me? Let's see. I started at some weird hour, and I'm actually close to the end of my period, if I'm not mistaken.
Yeah, your hour and a half has 3 minutes.
Yeah, that's not so good. Okay, so I better wrap up. So I actually missed then saying how you do 2 qubit gates, and I have to. I should say something about that. That 2 qubit gates are achieved by putting another transmon into the same cavity. And it hardly matters where the 2 transmons are. You have 2 couplings like this. And then there are various schemes involving either tuning the frequency of this transmon, really literally doing this axis, which you do with this DC squid trick, or by shining radiation in the right way. But you can, in fact, get a variety of entangling gates. So C phase is indeed achievable in this setting. These tricks became available about 4 years ago, and so the 2 qubit fidelities were 90% or so as of 2009, and with various tweaks and improvements and a lot of careful quantum control and taking care of pulse shaping and stuff like that, they're sort of 96% as of the published literature of the current time, and unpublished indicates that 99% is pretty near at hand. But that's about it. Putting a 0.9 here, the people doing the experiment say, no, I don't know. I have no idea how we're ever going to, or we need some new ideas of precise control to get that. So I realize those are just numerologies. I can't really explain that at the moment. IBM is pretty busy with that. I'd say they're the ones that are really on the top of this whole sort of high precision aspect of this work, sort of semi-metrological approach to this. They have the best, I should have said the coherence of these are not spectacular compared with the 3D cavities. So the transmons in this setting have reported coherence times which are a few microseconds, except at IBM where they seem to manage to get about 40 microseconds. They assure me nothing so profound, just they say they've been way more extensive in their understanding of the electromagnetics of any groups, just doing huge amounts of simulations to understand what are the real capacitances and so forth.
And that's in the 2-dimensional stuff?
This is in 2D, yeah. So they've really improved. They've gotten 2D numbers that 2 years ago would have been state-of-the-art 3D numbers. So that's, they say they've been able to deal with these dielectric losses. A lot of it had to do with how they processed the capacitors. So they simplified the capacitance processing. A lot of material science, basically. So, I shouldn't denigrate it. It's really hard work. I always say that material science is about as hard as pure mathematics and about as unpredictable. You just keep trying things and eventually, you prove the theorem, or eventually you actually find a combination of processes that work. And of course I can't end without saying that we can do surface code with these, so why not? Actually, it only involves one additional hardware fact, which is that in addition to having multiple transmons in one cavity, which is kind of trivial, you just grow them in different places in these gaps, you can actually have one transmon in two cavities at the same time. So in cartoon fashion, let's see how I want to do it. So there's a cavity, which remember is just sort of a straight line for me. And there's a transmon here. But it can at the same time be Jane's Cummings coupled to a different cavity. So you might wonder what's the actual metal arrangement that permits that to be true. That, in other words, to get a term like this, but now where you have to write an index, say I, for which cavity you're talking about, and you get, in fact, comparable and still strong, couplings simultaneously to both cavities. But there is, in fact, a metal arrangement that was worked out within the last couple of years where that is indeed true. It's slightly analogous. I mean, in optics, you'd have to think about some kind of crossing cavity scheme. An atom here, and it's in a mode of a cavity like this, and also a mode of a cavity like this. These wire cavities are way more flexible in how you can set up couplings. So, and then the last picture I was going to show then was a little artist sketch of how you would use this one additional, architectural capability to make a surface code. And so this is my proprietary surface code, patent pending, actually not patent pending, just written down in some fantasies. So these are all these one-dimensional cavities, but you're allowed to twist them around any way you want. So let's twist them around and make them this way. Let's have a whole array of them, in fact. And qubits, I'll stop being even vaguely realistic about the qubits. Qubits are just sort of pink dots. So here's a square arrangement of qubits and cavities. This arrangement is sufficient in the sense that it's an arrangement that has a setup so that looking from this qubit, its cavity coupled to qubits north, south, east, and west, so that you can do gate operations nearest neighbor square. That's it. There's nothing more to be said. You have the architectural elements of doing surface code. Now, what you do have, you have hard work to do in that you're supposed to get signals to, in and out of all sorts of places here to do this stuff. One fact is, and actually already presently explored, is this measurement can in fact come in from a completely different cavity. So you can, and it can be done in reflection also. So just one extra cavity tuned up to be just the right parameters to be a measuring cavity is actually a good thing, rather than double using these cavities for both measurement and for coupling. But the main difficulty is then that sort of in each square element of this, you have, several inputs and outputs that are needed. You have to do 1 qubit gates, 2 qubit gates, measurement. And so in this area, if you have your 1,000 qubits, as John Martinez has announced, you need thousands of input and output channels of wires that each of which in present day experiments involve its own devoted coaxial cable. So you have to think of this bundle of coax cables. And to me, this starts sounding like some CERN experiment. It has to get simpler than that to go really a lot further. And naturally, I'm being totally optimistic that when I say the fidelity is 99%, that's not good enough for surface code. Well, it's pretty marginal anyway. So this has to get better too, and the experimentalists are not really sure how it'll get better. But I'll be, this will be a really cruel turn of history if we've gone 6 orders of magnitude in the sort of measurement of this parameter, and we can't get one more order of magnitude. That'll be very weird to me and absurd. So, but how it will actually happen, I don't know. But that has to get some better, another 9 or 2 better, and the measurement fidelity has to be also in that order, and that's also not trivial. I mean, they're getting there. They're in the 90s in the measurement fidelity as well. And they have to figure out this whole real scalability, the real electrical engineering scalability of this. But that's the conceptual scalability, and that's the groups that are saying we'll do at Delft and at IBM. They say we'll do 13 qubits. It's really just a patch of this. That's what they're aiming for. So you can be looking for the papers for that in the next few years. Okay, so I think I'll stop. Thanks.